So, towards the end of wavelets, we have to understand the following, that there is a resolution that is happening at different scales, right, and there is a resolution in time. And what about in the frequency? Is the resolution the same in frequency, right? I mean, imagine I have a short burst of a pulse, right, and I can measure the burst, or I can measure some event of the signal in the variance of the signal in time, and some statistical properties of the signal in time, and can I have the same sort of resolution that I can get in the frequency domain. So, this is one of the questions that one would naturally think about. So, fortunately for us, somebody did investigation on this time frequency uncertainty principle. This follows akin to the position momentum uncertainty, Heisenberg's uncertainty principle that we are aware in quantum mechanics, right, and the same sort of idea exists actually in when we look at time frequency uncertainty in signal processing, and there is a more deeper theory using operators in mathematics, and will not get there. Okay. So, let us begin. Consider a finite energy signal, right. If it is a finite energy signal, which means integral minus infinity to plus infinity, I mean, you can put any range for this. I mean, this is very general. I mean, you really will not ideally reach minus infinity and plus infinity, but this is just for pedagogical purposes, and if you see some range, or you just have to put the appropriate range here in your definite integral. So, this energy is strictly less than infinity. Now, let us assume that the signal is centered around 0, I would say precisely at 0, both in time and frequency. That is, it is 0 mean. If it is not 0 mean, you can always subtract the bias and get it to 0 mean. Okay. Now, when we think about signals, we discussed in the very beginning of module 1, when we looked into signal geometry, that we can think about different kinds of averaging statistics. One is just a normal time average. You are given the samples, you compute all the statistics, whether it is mean or the variance or second moment, third moment, so on and so forth, right. You can compute all the moments across the signal, or you could do the statistical average, right, statistical average. So, let us look at the time average. Okay. Now, let us compute the variance in time and frequency by usual time averaging. Okay. Now, since we said we are dealing with 0 mean, we can compute the variance in time sigma t square as integral minus infinity to plus infinity t square mod s of t square dt, and there is a normalization factor here, which is the square of the L2 norm of the signal, right. And why should we do this is a question that you might want to ask. Why should I normalize? And if we treat the signal as a random signal, there should be some distribution over which we have to weigh, right. So, if you fold this norm inside, right, so you can basically rewrite this as essentially integral minus infinity to plus infinity t square mod of s of t square dt divided by the L2 norm. Now, can you appreciate that this is like your density, right? This is like your PDF, probability density function, because when you integrate this is basically this is integrates to 1, right. So, therefore, you can compute a second moment like this. Okay. Now, we will do this in frequency computing the variance in the frequency domain. We get sigma omega square is integral minus infinity to plus infinity omega square modulus of s of omega square d omega divided by the norm L2 norm over the spectrum, right. Again, you can interpret this as a density like what we did earlier, right. There is no big deal. So, this is also like you can interpret this as okay. So, now I think we are sort of set with our problem. Now, you can also think about in the notion of quantum mechanics, you can think about this as position, this is momentum, and you can think about these these quantities, and you are also looking at the variance here, right, or some other two set of quantities. Now, by Parseval's theorem from your undergraduate, norm s of t square, L2 norm of s of t is the same as s of omega square, right, because if you apply the Fourier transform, you are not going to alter the energy in the signal, otherwise it would be the transformation is useless if you lose energy, right, because of energy conservation property. So, notation wise this is easy for me, I can just write it like this, some norm of S square. I will get rid of t and omega, and I am saying norm of S square, because it is the same whether it is time or frequency. Okay. Now, let us consider the following product, which is the variance in time and the variance in frequency. I considered this product. This is essentially integral minus infinity to plus infinity t square mod s of t square dt times. Now, we can interpret the omega times modulus of s of omega as this quantity, because from duality, if you take d by dt of s of t in the frequency domain, it is you are multiplying by j omega, right, and the modulus will pull the magnitude of j to be 1, right, and you have omega square s of omega square, modulus of s of omega square, right. So, this is an important step, divided by power 4, because you have a norm s square for this term and another norm s square for this term. So, you have a power 4 in the denominator, and in this quantity it is basically due to Fourier transform property, right. If you take the Fourier, it is j omega, right. So, you have this additional this j omega quantity, which justifies what we have. So, now consider integral minus infinity to plus infinity modulus of I will say t square times s of t square dt. Consider this. This can be written, I can fold the t inside the modulus, there is no problem with it. So, I can write this in this form, modulus t times s of t square dt, and you can interpret this quantity as the L2 norm square of t times s of t. Okay. See how we are kind of building the logic, right, from starting from the variance to interpreting this into the norm. And similarly, integral minus infinity to plus infinity modulus of d by dt s of t square dt can be interpreted as the L2 norm of the derivative of the signal, right, L2 norm square of the derivative of the signal. Now, we have a product of two norms. So, your intuition should tell that there is Cauchy-Schwarz somewhere kicking in. Okay. So, let us apply Cauchy-Schwarz inequality. So, the result states that if you look at the norm of two functions that are possibly complex, then the modulus of the inner product square is basically less than or equal to the norm square of the product of the individuals. Okay. Now, using this we can say, I will say this is relationship A, using A we can write sigma t square times sigma omega square as a quantity which is greater than or equal to, because now it is existing in product form exactly. So, therefore, the inequality is this way, right, 1 over norm of S L2 norm of S power 4 times I bring the modulus integral minus infinity to plus infinity t times S of t times, there is one careful observation that you have to make, where I am bringing in the conjugate of this signal under the Hermitian inner product form. Now, this quantity that we have, modulus of some integral square. So, this can be a complex quantity. So, we can simplify this little carefully. So, this is 1 over the norm of S power 4 times I can write the absolute value of the real part of this integral t times S of t times d by dt of S of t bar dt square. Why? Because for complex numbers, modulus of real of z is certainly less than or equal to modulus of z, right. This is a straightforward result. So, you take just for a cross check 3 plus 4j is that vector, the length is 5, the real is 3, and when the complex part is 0, then it coincides with equality. So, you have this relationship. Now, real part of some complex quantity z can be written as 1/2 z plus z conjugate. This is a straightforward result. Now, consider the real part of this integral minus infinity to plus infinity t times s of t times the derivative of the signal conjugate dt. Right, I can write this as 1/2. I will pull the t factor outside because it is just a scalar, its time variable, it is a scalar, right. So, you can write it as s of t times derivative of s bar of t plus s bar of t derivative of s of t, right, using this rule, using this step 1/2 of z plus z conjugate. I just did that here, right. So, I just take this as my z here, I just conjugate it. I will no, I will come to the point. I am just yeah, I need the integration there. Yes, the real part. So, I just have t times, I am looking at this term here, I am just rewriting this thing here, and I just have to put if you are okay with it. I am just focusing on this term, just the argument of the integral. Okay. Now, let us focus on the term within the integral. Okay, let us focus on the term within this integral. So, this is basically, I would say, term within the integral is basically half t times d by dt of modulus of s of t square. Why? Because you can write modulus of s of t as s of t s bar of t. Now, you take the derivative using chain rule and it automatically comes. Okay. So, therefore, sigma t square times sigma omega square is greater than or equal to, now I have to square this quantity, right, it is 1/4. I have a norm s power 4 and then I have an absolute value here, then this integral minus infinity to plus infinity t times d by dt of modulus of s of t square dt. Now, still it looks complicated. Let us consider integral minus infinity to plus infinity t times derivative of modulus of s of t square dt and perform integration by parts, right. We have the familiar, this is what I recall from my high school IIT. This is inverse function, logarithmic, so on and so forth, right. You use that, last is exponential. So, you apply this rule, integration by parts. So, what we get is t times s of t square minus infinity to plus infinity minus integral right, because I take the derivative, I integrate that, I get this, and then I differentiate time, then I get 1 there, right. First function integral of second function minus integral of second function derivative of the first function. Okay. Now, this quantity goes to 0 and this is basically interpretable as negative norm of s square. Therefore, sigma t square times sigma omega square is greater than or equal to 1 upon 4 times minus norm s square. I need to square this quantity because I have that modulus of that integral square is what I have. So, this is basically just 1 by 4 because norm s power 4 and norm s power 4 cancel in the numerator and denominator, right. It is a very interesting result. I mean, it is a very interesting result that you look at the variance in time and the variance in frequency, and that is lower bounded by 1 upon 4. Take any signal, any s of t, it is at least this much that you will live with your uncertainty in your measurement in time and your measurement in frequency. It is a very profound result, and this result was proved by no less than the Nobel Prize winner Denis Gabor, who is the father of holography. So, let us say the roots, this is originally proved by Denis Gabor in 1946, and of course, Denis Gabor was great in many areas including in signal processing. It was a signal processing result, but of course, he is a father of holography. So, now we have a very important principle, uncertainty inequality or uncertainty principle in signal processing, that we cannot simultaneously localize in time and frequency no matter what. So, a follow up question arises, when does this equation, when is the inequality satisfied with equality, or when is the equality satisfied, when can we get this actual limit of 1 by 4. So, for this we ask the next question, when can we achieve equality, that is sigma t square, sigma w square, sigma omega square equals 1/4. I need to get to this lower bound. Now fortunately we have a solution from Cauchy-Schwarz again that we are comfortable. We can say it happens when t times s of t is some constant k times derivative of s of t. Right, I assume at the moment I just will remove the conjugation here and I will just assume s of t, assuming real signals. Now the k is this factor, right. I mean when this is k times the derivative of s of t, then this is equal, the inequality becomes an equality, right. Now we have a differential equation here. So let us group the terms and integrate both sides. So how we do this? We say derivative of s of t by s of t is t upon k times dt, and then I need to do an integration on both the sides. Okay. So if I integrate, I get log s of t is t square upon 2 times k plus some constant of integration. Now s of t is of the form e power t square upon 2 k plus some constant, which is, if you write it carefully, it is e power times c times e power t square upon 2 k. Let me call this as some constant a times e power t square upon 2 k. Well, we have done the integration, but let us see if things are making physical sense for us, right. So if you recall, in the very beginning I said let us consider finite energy signals. Now I have a solution, s of t is of this form, a times e power t square by 2 k, and if you let k to be a positive constant, the energy in s of t would be infinite, potentially could be infinite, right. So therefore if s of t is to be a finite energy signal, then k must be a negative real number. Okay. So therefore let b equals minus k, right. Let b is some negative k. So if I did that, then s of t is some a times e power minus t square by 2b. Now this is easy for us to think about, because this is like, has the form of a Gaussian pulse. you are not making it a distribution. I mean if you want, if you can choose a to be 1 upon root of 2 pi b, then it becomes like a distribution, it integrates to 1, otherwise this is just a Gaussian pulse. Now this basically led to Gabor transformations. So this form led to Gabor transforms. I mean I am not going to deal with Gabor transforms. I mean if we were to go into more details of time frequency analysis, we would start possibly with this as our first step and then go into the details. Okay. So, but and you can also appreciate why you think about the Fourier transform of a Gaussian pulse, why this has the same shape, and Gaussian has very interesting consequences. One of this is this uncertainty relationship. The Gaussian PDF has the maximum uncertainty. If you look at the differential entropy, right, and evaluate this for the Gaussian PDF, it gives you the maximum uncertainty, right, and that is the reason why people look into Gaussian PDFs, you know, when in their study of signals with noise and particularly noise having Gaussian PDF. And Gaussian PDF again comes from your central limit theorem results. So somehow whether it is consequential or it just nature is providing you that way, it is just there are a lot of very interesting properties with Gaussian, whether it is a distribution or a pulse or a transform or whatever it is, and you see this again and again in signal processing and information theory. Okay. So we'll stop at this stage. I think this is something which you have to really understand, and before we conclude, I would sort of give you a homework problem to ponder. Ponder on how the time frequency uncertainty principle applies in the context of wavelet decomposition at different scales. So we have studied the wavelet decomposition and reconstruction. So at every stage of wavelet decomposition we have a certain resolution, right, it is a time resolution. Now think about if this transformation can meet this bound, or how close or how far away is it from the uncertainty principle if you were to do localization through wavelets. Okay, this is something to think about. This may or may not appear on the exam, but there is a hint for you to think through this homework exercise. So we will stop here and we can go through questions. Okay.